this video we will learn one interesting but very technical topic of testing of hypothesis for comparing two population means. And since we are concerned in drawing inference about two population means in this video, so we will deal with two populations and then two samples drawn from them. This video will further explain three different type of tests: pool t-test, prime t-test and pair t-test. All these three t-tests are used compared to population mean. We will look at different scenarios where these tests are used, and this video will guide you step by step with the help of examples that how and when to choose which test. First of all, explain the concept of independent and dependent samples, and then we will look an appropriate test. We will further look at whether the population variances are equal or they are not equal, since we have to pool the sample variances based on this information. So stay there, you will learn a lot in this video, and we will denote them just like here. You can see on your screens population 1 and population 2. From population 1, we may denote the population parameters mu1 and sigma1 scale. They are unknown quantities calculated from the population 1. Population parameters came from population 2. And we need to draw inference about these unknown numbers, the mu1 and the mu2. In this specific scenario, we are interested in drawing inference, but mu1 minus mu2 is equal to 0, meaning that both population means are same. Both population means are same. And we will definitely draw a sample from population 1 that will be denoted as n1, and then the sample from population 2 that will be denoted as n2. Similarly, we will have some calculations from sample 1 and sample 2 simultaneously, and we will call them x1 bar. X1 bar represents the sample mean from the first sample. X bar 2 represents the sample mean from the second sample. And then similarly, S1 square is the variance come from the first sample, and S2 square is the variance came from second sample. And we will definitely use x1 bar minus x2 bar for drawing inference about mu1 bar minus mu2 bar. This screen is showing you some of the terminologies which will be used in this video later on. So you have to get in your mind that there are two populations, and we are going to draw inference about the difference of the mean from two populations, that is mu1 minus mu2. Okay, look, if we are interested in finding mu1 minus mu2 equals 0 or testing mu1 equals mu2, similarly we may be interested in finding something like this: mu1 minus mu2 is equal to, for example, 10. This statement states that the average in the first population is more than the average in the second population by 10 unit. So this is also on card. So we will call it the testing of hypothesis about difference between two population means. Now let us just talk about two different possibilities of a sample, or two different scenarios in a sample, because you are going to draw samples from two populations, and samples they may be independent in some cases, or they may be dependent. We will just draw a line. We will just see what is the difference between independent and dependent sample, and keep in your mind that this is a really important part to understand in choosing a right test, because once you determine that the samples are independent, the type of test is slightly different as compared to the dependent sample. So let us just go through the introduction to independent samples. We'll just start from an example. Look at the bottom, comparing two teaching methods, that method 1 and method 2, on two different groups of students. Remember, two different group of students. This is really important, that section A and section B. Section A, so method 1 may be tested on section A, and then the method 2 may be tested on section B. The students in section B and students in section A, they are not same. This is really important here. So the data came from here will be the first sample, that is x1, maybe the marks coming from the students in section A, and the second sample x2 may be the marks of the students coming from section B. We will call them unrelated group because the first group is in no way related to the second group. Or sometimes we call them unpaired group also. They are not paired. The observations in the first group, they are independent from the observations in the second group. Or the individual in the first group, they are different from the individuals in the second group. Students in section B and students in section A, they are different individuals. We call them the independent samples. So going to the second type of sample, that is dependent sample. They are related groups, also called paired groups. That is why we sometimes call this test as paired t-test. So just focus on the example here, comparing the cholesterol level of same patients over the period of 2 different times. For example, you are comparing the cholesterol level of same group of patients, one reading taken in January 2020 and the second reading has been taken in March 2020. This data of January may be denoted as x1, the first sample, and this data may be denoted as x2, the second sample taken in March. But here you see the individuals in the first group are same as that of individuals in the second group. So this makes the sample dependent sample. So we will have to draw a line here between independent samples and dependent samples. Okay. The independent t-test requires, I mean to say that if the samples are independent, then the response variable means the data which you will collect from section A and section B. That is called your response variable. That should be approximately normally distributed within each group. This is an assumption of using this test. And similarly, for the pair t-test, that also requires that the response variable in that case is also approximately normally distributed. For example, here you note that cholesterol level. So cholesterol level of the patient, that should be normally distributed for using this dependent pair t-test. Okay, to understand the type of samples very carefully that we have just described in the previous slide. After looking at the type of samples in the previous slide, we will look at what kind of test we are going to apply if the samples are independent or if the samples are dependent. In case of independent samples, further we will look at their population variance of the both populations. If the population variances in both populations are equal, then it will be a different scenario for us, and if the population variances are not equal, we will see it differently. So first of all, if the population variances are equal, here is the formula which we will use here. X1 bar minus X2 bar minus mu1 minus mu2 and divided by 1 over n1 plus 1 over n2 multiplied by s square p. This s square p is the pooled variance. I mean to say that we will pool the variance of both groups, of both samples to use here. Why we will pool them? Since the population variances are equal. So if the population variances are not equal, then we will not pool the sample variance. So this is the only difference. And look, how will we pool it? This is the formula. This is the sample variance from the first sample, sample variance from the second sample. N1 is the sample size in the first group, N2 is the second group sample size. So this is the formula by using which we will pool the two sample variances, and we will use it here. We will also call it T-pool test because of just pooling the variance in both the groups. Now let us go to the second portion where the population variances are not equal. The formula is same, just the difference is that we will not pool the variances here, and rather we will use variance of the first group and variance of the second group separately. Will not pool it since the population variances are not equal. Now an important part is that how do we know that whether the population variances are equal or not equal? We have a separate test for that. We can test whether the population variances are equals or not equals on the basis of sample variances. We will see in a separate video that by using F test you can test the equality of two variances. Okay, going back to the second case when the samples are dependent. So if the samples are dependent, the only test we're going to use is t-pair test. We call it t-pair, and we will take the difference of two samples like x1 and x2, for example. There are the two samples taken from the same individuals, they are paired values. We will take their difference, and difference will be denoted as d, and that difference we will use in pair t-test. Right, you are seeing here d will come from the difference of two samples. Why will we will take the difference here? Since they are dependent samples and they are paired observations, we will take their difference and denote it with d, and then we will use d for the further testing. And this formula is similar to the one which we have used for testing of hypothesis for single population mean. Just the difference is that over there we have used the sample, denoted the sample with x. Here we have difference of two samples and we denote it with the d. Well, since this is a t-test here, so we will also have to talk about their degrees of freedom, because we need degrees of freedom for having the table values from the table. So in each case we will see how we will calculate the degrees of freedom. If the samples are independent, and same scenario, if the variances are equal, the degree of freedom is n1 minus n2 minus 2. It is quite straightforward that in pool t-test we will use this degrees of freedom n1 plus n2 minus 2. And if the variances are not equal, then we will use this formula to calculate the degrees of freedom. This is just a little bit complex formula for calculating the degrees of freedom. The answer of this formula may not be an integer, so we will round that number. For example, if the answer in this case somewhere comes like this 7.45, we will consider the degrees of freedom as 7, take the integer part. And then if the samples are dependent, the degrees of freedom is n minus 1, straightforward, because we will take the difference of two samples and we will be dealing with only the difference variable, that is d. So in d, the number of values will be considered as n, and the degrees of freedom will be calculated as n minus 1. First of all, I will explain the concept of t-test when the samples are independent. So this is the first case which we are going to discuss, the independent samples, and also population variances are equal. So remember, whenever the population variances are equal, we will use pool variance, and we will definitely pool the variances of both the samples here. And what we are going to test here, that equality of two population means, or we can even write them as mu1 minus mu2 equals 0. This is one and the same thing. Okay, here is the hypothesis which will test this statement, mu1 is equal to mu2, the H0, the null hypothesis, and definitely the alternate hypothesis is in this case a complement of H0 as always. These two hypotheses, the H0 and H1, they are exactly complement to each other. And this is a two-tailed test, since the alternate hypothesis contains the sign not equal to. Based on this sign, we will determine which type of test it is. So in this case, it is a two-tailed test. The second step is to specify the level of significance, that is alpha. I have explained this concept of alpha in the previous video when I was doing on testing of hypothesis for single population mean. However, alpha is the probability of rejecting the null hypothesis when it is actually true. So the third step is the formula and the rule which we will use to calculate the value from the sample. The x1 bar minus x2 bar, well, we will take the difference of these two sample means and then minus mu1 minus mu2 divided by all terms, you know it very well. This is pooled variance, and why we are using pooled variance here? Because the population variances are equal. So if we know that population variances are equal, we will apply T pool test and we will pool the variance of both the samples. In other case, we will not. And the pooled variance, the formula for the pooled variance is this one, where we will add the sum of squared deviations from the first sample and sum of squared deviation from the second sample divided by n1 plus n2 minus 2, and in this case degrees of freedom is n1 plus n2 minus 2. So fourth step is the calculations involved in this question. So if you have both the samples, you will have to calculate their means. You will have to calculate their variances, and for the calculation of variances you have to pool them also, since it's a pool t test, and after all those calculations you will finally get the value of t. So fourth step will be the calculations. Fifth step is the most important step, that is the decision rule. Since it is a two-tailed test, so we will divide our alpha, that is 5%, equally amongst two tail, that is alpha by 2 on the left tail and the alpha by 2 on the right tail. So if I divide alpha here, in this case divided by 2, so 0.05, this is my alpha for this question. I just divide it with 2 and I get 0.025, the answer. So it means I will place this area on the right tail as well as on the left tail. So as if I sum the area alpha by 2 and alpha by 2 both on the left and right tail, I will get exactly the alpha. The remaining area inside the curve is 0.95, since the total area under the curve is 1. This is important to know that. So we need in this case we need these two critical values. We call these critical values T alpha by 2, and on both sides we call them T alpha by 2, whereas on the left side of the distribution we place minus sign with it, since the T distribution is symmetric around 0. So anything below the center will be marked with the minus sign, anything above the center will be marked as plus. So one side this T value will be positive, on the other side it will be negative, since the T distribution is symmetric around 0. Our rejection region of the null hypothesis on the both tails now. So we have two critical values. If for example our calculated value from the step 3 will be greater than T alpha by 2 or it is less than minus T alpha by 2, in both cases we will reject the null hypothesis. So otherwise we are unable to do so. So going to the step 6, here we have to make a decision about the null hypothesis. So finally at the last you also have to integrate your conclusions with your problem. This is the most important, because just saying reject H naught will not make any sense. So whatever the question is, whatever the problem is, finally you have to integrate your results with that problem. This is an example of the same scenario. If you go through the example, you see there are two samples given, and this example is from the engineering field, the strength of ropes made out of cotton yarn and coir. So two type of yarn, and the strength of the ropes have been taken. So a sample values of 5 are in cotton category and the 5 are in coir category. So we have two different samples, 5 values from the cotton group and 5 values from a coir group. Test whether there is significant difference. So we need to test the difference in the strength of the two types of rope. So we are to compare here two broader groups. One is cotton, one is coir. So we will compare them. Their strength, that whether there is significant difference among two groups. Okay, at 5% level of significance, so alpha is also given. And the last statement, assume population variances are equal. So this question is all about independent samples and population variances are equal. So definitely we will use T pool test here. Why pool? Since the population variances are equal and the samples are independent. So the pool T test is the right approach here. So let us just go and build the null hypothesis and then the alternate hypothesis. Here we go. The null hypothesis states that the strength of ropes made out of cotton yarn, the first group, is equal to the strength of ropes made out of coir yarn. So this hypothesis, the null hypothesis, states that there is no difference among the strength of ropes in both groups, whereas the alternate hypothesis says that there is significant difference among the strength of ropes made out of two different yarns. So let us go ahead with this example. Alpha as given, 5% means 0.05. The third step is to write the formula. Since it is an independent sample and it's a pool test, so this is the formula which will be used in this question. So x1 bar is the sample mean that we will take from cotton group, since we have put the notations x1 to the cotton group, x2 to the coir group. Well, group 1 and group 2. So x bar will be the sample mean taken from the x1 variable, x2 will be the sample mean taken from x2 variable. Mu1 minus mu2, well, it will come always from the null hypothesis, this number, because null hypothesis we can write it as I have earlier explained, that we can also write this like this. Mu1 minus mu2 is equal to 0. So this can also be written like this. So in this case mu1 minus mu2 is 0. So let us just go to the denominator of this formula. It is a pooled variance, and n1 is the sample size in the first group, that is 5, and 2 again the sample size in the second group. In this case sample size of both groups are same. Well, it is not necessary for all the questions where the pool test. Now the formula for the pool test is something like this. Well, we can also write the same formula. The pooled variance is equal to n1 minus 1 s1 square plus n2 minus 1 into s2 square divided by n1 plus n2 minus 2. So both these formulas will produce the same result for pooled variance, as this number right here is the sum of squared deviations from first sample, and this sum of squared deviation is equal to this n minus 1 into s1 square. So let us see the calculations involved in this question. Here we go. We have written both samples and take the aggregate. This is the sum of x1 39, sum of x2 41. We will divide both these sums with the sample size to get the mean, x1 bar is 7.8, x2 bar is 8.2. We will use these two means for taking the deviations, that is x1 minus x1 bar. Look this column, x1 minus x1 bar. This is known as the deviation of the first sample from their mean. So all these deviations, if I look at them, this will sum up to 0. This is the property of arithmetic mean. So taking the square of these deviations, by doing the square of these deviations, I would be able to get the sum of square deviation for the first sample. So taking the square of all values, this 2 square is 4, 2.8 square is 7.84, and so on. The sum of the square deviation from the first sample is 16.26, right? And similarly, we will take the sum of square deviation from the second sample, that is x2 minus x2 bar. X2 minus x2 bar means we will subtract the mean 2, that is 8.2. We will subtract mean 2 from each value of x2, like this value 0.1. This is produced by just subtracting the second sample mean from the first value, like 8.4. This 8.2 is the mean of x2, and this 8.3 is the first value, like here. So taking all the deviations, and if we are going to add the deviations, this again will be 0, and in the second step we will take the square of these deviations down. We need the sum of square for both variables. This is 13.63. By using these numbers, the sum of square deviations, we will calculate the pooled variance now. The pooled variance formula I have written here, and you know that the 16.26 and 13.66, the values will come in the numerator of the formula, and then n1 plus n2 minus 2 in the denominator to get up the pooled variance as 3.74. Now we will use this number in calculating the T pool value. Look, the formula for T pool value, and placing all the data, all the information, mean 1, mean 2, that is we know that 7.8 and 8.2, and this difference, as I already pointed out in the previous screen, that this is 0, and here is the pooled variance, and the first sample size 5 and the second sample size 5. Okay, by solving it you get minus 0.33. Now remember, it was a two-tailed test, so as it is a two-tailed test, so we need to mention here that the rejection region for it. Here we go. Look at this curve. This is the T curve. As we have already know, this T is symmetric around its center, and on the left side of the center you have values with a negative sign, and on the right hand of the center you have values with a positive sign. So we need these two critical values, T alpha by 2 in positive and T alpha by 2 in negative, since it's a two-tailed test. So as we have already specified that our alpha was 0.05. So by dividing this alpha by 2, we get 0.025, and we place alpha by 2 here on the left tail and the remaining alpha by 2 on the right tail. So these are our rejection region on both the tails, the right tail and the left tail, since it is a two-tail test. So I have highlighted the rejection regions on both tails. So anything below this number, minus T alpha by 2, or anything above this number, the T alpha by 2, will leads us to reject the null hypothesis. Otherwise we will not. So same is the case I have written here. I will just show how to take the table value of T, like how this value have been taken from the T table. We'll explain it in the next screen. For the time being, just take it and just make a decision. So our T value is 0.33 with minus sign. So we will have to look at whether this T value is below this critical value minus T alpha by 2, or it is above this critical value. So this is somewhere in between. So this is not less than minus 2.306, or this is not greater than 2.306. So it means that since our calculated value did not fall in rejection region. So there are two rejection regions, this one and this one, but our critical value did not fall in both of them, so therefore we are unable to reject the null hypothesis. So if we are unable to reject the null hypothesis, what was there in the null hypothesis? Null hypothesis states mu1 equals mu2, that is strength of both the ropes are same, there is no significant difference. So if we are unable to reject the null hypothesis, our conclusion is there is no difference among the strength, or we can say that same strength for ropes made out of cotton and coir. So let us just see how this table value have been derived from the T table. So as we already know that in the last example we had alpha as 5%, and then if we divide that alpha by 2 we'll get 0.025 now the degrees of freedom. So these three numbers are really important for having the table value from the T and the alpha, and if it is a two-tailed test, alpha by 2 value and the degrees of freedom. So here we go with the T table. As we know that by dividing the alpha we get the column, this column 0.025, and with respect to the degrees of freedom, here is a row, the 8th row. So our value is 2.306, like this is the column, and here we go with the row, the value is 2.306. So this table value will be changed based on the value of alpha and based on the values of degrees of freedom. So degrees of freedom and the alpha, they both are very important for picking up the right value from the table. So here we go with the graph. Since T is two-tailed, so we have to place this value, the 2.306, with the positive sign on the right tail, and the same value with the negative sign on the left tail. So these are the two critical values for our test which we used in the last screen in the first example, as you have already seen. So let us just move to the second example here. In this example we will just go through a little bit faster here, since we have already mastered all the steps involved in testing of hypothesis. This data is all about 20 students statistics course and from section A. So 20 students from section A, 15 students in the same subject, section B. So we have two sections, section A and section B, and the average marks of 20 students from section A are 50 with standard deviation 2, and average marks of 15 students taken from section B are 47 with standard deviation of 3. On the basis of above sample information, so the example states that the above provided information is a sample information. So section A will have a lot of students, and 20 students are randomly selected from section A, whereas 15 students are randomly selected from section B. So we have two samples here. They are independent, since the number of students in section A and number of students in section B, there is no dependence among them. Similarly, we can see the population variances are equal. So again it is a pool test. So how to construct the hypothesis? Let us just go ahead and see how will we construct the hypothesis here. In this case, we conclude that students of section A perform better than the students of section B. So students of section A will only perform better than students of section B if average marks of section A exceeds the average marks of section B students. So we will write the hypothesis just like this: mu1 is greater than mu2. Here we can see the performance of section A students is better than section B students. So this is our alternate hypothesis, since there is no equality sign with it. As a complement, we will write the null statement, that is mu1 is less than or equal to mu2. Here the alpha, if not specified in question, we will take it 5%. With T pool, the same formula as you have already seen. Similarly, the pooled variance. Now just look at the calculations. Here we have to do less calculations, since the sample means and sample variance, they are given in advance. So this information is already given. the mean and the standard deviation. We will make the variance out of standard deviation. Simply squaring it, we will get the variance. Simply squaring the standard deviation and we will get the variance of the second group. And here we go with the formula of pooled variance. While replacing all this information which is given in the formula, we calculate the pooled variance as 6.12. Now we will write the formula for T, and by putting all the values that is given above in this formula, we get the value of T. The value of T which is calculated from sample is 3.55. Now we have to move towards the critical value, the table value, and the decision rule. The most important concept in testing of hypothesis, it is the right tail test. Why it is right tail test? You see, in the alternate hypothesis, we have written mu1 is greater than mu2. So this greater sign is indicating that the test is right tail test, right? So it means right tail test mean if your alpha is 5%, if your alpha is 5%, all your alpha will go to the right tail right here. So we will be shading this area. This is the rejection region for our null hypothesis. Rejection region for our null hypothesis. So what was the area left behind this? All this. This is 0.95. 1 minus alpha. If alpha is 5%, so this is 0.95. So this 0.95 is the area where we cannot reject null hypothesis, whereas this is the area where we will reject the null hypothesis. And this line is in between the rejection and acceptance of null hypothesis. We need this critical value, the 1.693. The question is from where we will get this critical value. We will show you in the next screen that how we have taken this value from the T table. For the time being, stick with it, 1.693. We will compare this value 3.55 with this table value, and anything greater than the table value will leads us to reject the null hypothesis. In this case, clearly you can see the value 3.55 is greater than 1.693. So therefore we will reject the null hypothesis, and rejecting your null hypothesis means that the average marks of section A is significantly greater than section B. We are finally going to conclude that the average marks of section A is significantly greater than the average marks of section B. If you are going to reject your null hypothesis, for example, if you are able to reject your null hypothesis, it means your results are significant. Significant means here that you are concluding the H1. Here we go. Now, how have we taken that right tail value from the t-test? Alpha was 0.05. We will not divide alpha by 2 in this case now. Degrees of freedom here is 33. So, if you just scroll down your table, you will find that the value of 33 is not there. You have degrees of freedom 30, and then you have degrees of freedom 40. For some tables, you may have the value exactly for 33, but for some tables you don't find that value. Now how will you get this value for your test right now? So here we go. This is the column, so your value will be between somewhere here, right? Between 30 and 40, somewhere here. Notice that in the column the critical values have been decreased. So 1.697, and then for 40, 1.684. Although there is not a significantly large difference between these two values, but however, we will take their difference. We have taken their difference, and we have seen that the value have been decreased by 0.013 from 30 to 40. So this is this difference we will divide it with 10. Why 10? Because one value is for degree of freedom 30 and one value is for degree of freedom 40. So we will divide it with 10. This is the unit difference now. Unit decrease. So in order to get the value for 33, we will multiply this unit decrease with 3, and finally we will add. Look, here is an addition, not multiplication, right? Here is an addition. 1.697 plus minus 0.0013 multiplied by 3. So this minus answer, we will add this minus answer to 1.697 in order to get a critical value. However, to avoid this sort of complexity, you can take the value against degrees of freedom 30 also, because in this question our calculated value is far greater than these two values, that is 3 point something 3.55 to be precise. And here we go, the distribution. So this value which we have calculated and taken from the table, we will place it here, because above this value is our rejection region for H naught. This is how we will take the table value for the right tail test. Okay, going to the second scenario of independent samples where the population variances are not equal. Well, in this case where population variances are not equal, remember we will not pool our sample variance. That is the only difference. Here we go with the 6 steps, that is the null hypothesis and the level of significance and the formula. Just notice here, we will not use this pooled variance. Well, pooled variance, we will not use this pooled variance here. This is the only difference. We will straightforwardly use the sample variances taken from both samples, and this is how we will calculate the degrees of freedom here. Remember, if our degree of freedom turn out to be something in fraction like 7.45 or 7.58 or 9.2, we will take the integer part in this case and ignore the fractional part, since the degree of freedom should be integer. So we will calculate our degree of freedom by using these formulas. Here we go about the decision rule. Since it's a two-tailed test, no change in the decision rule. It is the same as we have already seen. Okay, going to the example here. This is the example taken from agricultural sciences, that is 6 horses were fed on diet A, 5 on diet B. So there are in total 11 horses. So there are two different type of diets, and we need to test whether the gain in weight, look at the hypothesis. Can we conclude that the diet B is better as compared to diet A? So we need to compare two diets, and for that purpose we have 11 horses as a sample, 6 in the first group, and we put 5 horses to the second group. After feeding both diet A and B, after certain period of time, we have noted the gain in weights. And these are the gain in weights, sample diet A and diet B. So as we have already mentioned in this question, that assume population variances are unequal. So if this is unequal, it means that this is not a pool test. So this is a prime test. So we call it a prime test. Okay, first of all, you need to write the hypothesis. So just read out the statement. Can we conclude that diet B is better? Diet B is better means that average gain from diet B will be greater than diet A. Or another way we can write that average gain with diet A is less than diet B. So we can write this hypothesis in this way. Look, this statement in H1 states that the diet B is better than diet A, or average weight gain with diet B is greater than diet A. So it is a left tail test in making here. By writing the hypothesis, we will maintain the sequence as the first group, that mu1, we write mu1 at the first slot and mu2 in the second slot. And since diet B is better, so we will revert the sign, that is mu1 less than mu2 means that average 2, mu1 less than mu2 means that the average in the second group is greater than the first one. That is what we want to test here. Okay, going with alpha 5%, and this is the formula which we are going to use, and I will show you the calculations quickly here. This is the calculation for the degrees of freedom. Okay, here are the calculations needed for this group. Since we have 5 horses for second diet, so one value will be empty here. 6 observations are in first sample, 5 observations are in second sample. We can calculate their means by dividing their sums with the number of observations in that group, and by using these arithmetic means we can calculate their deviations and the square deviations. Since we need the sum of square deviation, this number 88, we need them for calculating the variance. Similarly, with the help of the mean in the second group, we can calculate the deviations of second variable as well as the square deviations in that group. After taking the sum of the squared deviation second group, we got 120. So we will use these two numbers, 88 and 120. Just stick with them. We will use them in calculating the variances of the two groups. Here we go, the formula for the first group variance. Divide this 88 by n minus 1 and 1 minus 1 rather, because in the first group you have a sample size of 6 minus 1. And similarly, the variance for the second group, this 120 will be divided with n2 minus 1. Since the sample size in the second group is 5, so therefore 5 minus 1 will come in the divisor of the variance of the second group. So we get the variance of the first group and variance of the second group. That's what we all need here. Put those values in a t prime test. After solving, we get the value 1.34. Now this value will be used to decide whether we are going to reject the null hypothesis or we are going to retain it. So let us see, this is the left tail test. Why it is left tail test? Since our alternate hypothesis was mu1 is less than mu2. Since the less sign here in our alternate hypothesis direct us that this will be a left tail test. So this is the most important part in testing of hypothesis, is to find the critical value. So we will put our alpha on the left tail now, since it is a left tail test. And the left tail and right tail are one tail test, so we will not divide alpha by 2 here. Just put the complete alpha on the left tail. This is our rejection region, the shaded part in red. This is the rejection region. So we need this critical value, this one. We call it minus t alpha, and we have taken it from the table. I will show you in a couple of minutes. For the time being, take it minus 1.895 as critical value. So if our value 1.34 with minus, if our value is less than this critical value, then we will reject the null hypothesis. Otherwise, we will not. This is the rejection region. If our value is less than the table value, only then we will reject the null hypothesis. The degree of freedom here calculates to the 7. I will show you in the next slide that how will we calculate it. So since the calculated value for t did not fall in rejection region, because 1.34 with minus sign is not less than this number, So if it is not less than this number, we are unable to reject the null hypothesis. We cannot reject the null hypothesis here. So we can say that the sample did not provide evidence at 5% level of significance to reject the null hypothesis. So in other way, we can say that we are unable to reject the null hypothesis based on the information contained in the sample. So if we are unable to reject the null hypothesis, what was there in the null hypothesis? Null hypothesis states something like that: mu1 greater than or equal to mu2. So it means the gain in weight with diet B is not more than diet A. This is how we have taken that table value which we used for degrees of freedom 7 and for alpha 0.05, 1.895. This was the table value. This was the table value taken from the table, and this is how we will place it. So regarding the calculations of degrees of freedom, we use this formula. Look, W1 is S1 square over N1. W2 is S2 square over N2. So we have put all those values here. After solving, we get the answer 7.4. And since the degree of freedom is the integer part, so we will take the degree of freedom as 7. And against 7, we have seen the table value. This is how we will calculate degrees of freedom. And finally, we are moving towards the last scenario where our samples are dependent, where we have paired observations, dependent samples. We will now look at how to perform the testing of hypothesis for comparing two means in case of dependent samples or in case of paired observations. Let us just go through the example. The amount of lactic acid. Now this data which you can see here are the lactic acids in the blood which was examined for 10 patients. So with the result in the following table, before and after a strenuous exercise. So we have the 10 values for lactic acids in the blood before exercise, and then we have observed the same patients over a period of time after strenuous exercise. We again measured their lactic acids in the blood. So x1, the values, the lactic acid in the blood that have been taken before the exercise, whereas x2, the values for after is the lactic acid in the blood which was taken after the strenuous exercise. So what we want to do is here test if exercise changes the level of lactic acid in the blood. We need to test whether the exercise changes the level of lactic acid in the blood. So first of all, in case of dependent samples, what we need to do is to take the difference of both samples. This is really important step to start with. Take the difference of your samples after minus before, and we see the difference like this is 33 minus 15 equals 18. So this is how we will take all 10 differences. After taking the difference, we sum the differences, that is 124. We will take its mean. Now this is the mean of difference, 124 divided by 10, 12.4. Similarly, by using this mean d bar, we will calculate the deviations d minus d bar. The sum of these deviations will definitely be equal to 0 as the property of arithmetic mean, and going further, we will take the square of this deviation, d minus d bar square. Now this square deviation will be used to calculate the variance of the differences. This is the formula for the variance of the differences. Just in case you have confusions with this formula, just replace the d with x. You have already calculated the sample variance for x values or for y values. Just take the d values here and take their standard deviation, their variance. So sum of d minus d bar square over n minus 1. So n is now 10 minus 1, since you have 10 patients for which you have measured observations before their exercise and after their exercise. So this is dependent sample. So by this formula you will calculate the variance by just dividing this number. This is sum of square deviation with n minus 1. N is 10 here. So n minus 1 means dividing it with 9, we get 63.16. So we have d bar and the variance of d, the differences. So let us just go through the 6 steps of testing of hypothesis. We just need to measure the change. We write our hypothesis like this: mu1 minus mu2 is equal to 0. If just focus on the null hypothesis, mu1 minus mu2 is equal to 0 means that there is no change, that exercise did not bring any change in their lactic acid. Whereas H1 states that mu1 is not equal to mu2 or mu1 minus mu2 is not equal to 0. It means that the exercise have changed their lactic acid. So before and after values, they are not same. So we can write it like mu of d, that is mean of difference. This is mu1 minus mu2. So this difference we denote it with mu d, and we may write the same hypothesis in the form of mu d is equal to 0 and mu d is not equal to 0. Let us just go to the second step here, that is alpha 0.05 means alpha 5%, and the formula d bar minus mu d divided by s square of t over n. All these values we have calculated. This is 12.4. The variance of the differences was 63.16, n is 10, and this mu of d we will take from here, it is 0 in this case. So putting all these values in the formula, we get the calculated value of t, that is 4.93. So this calculated value 4.93, this will determine that whether we are going to reject the null hypothesis or we are going to retain this null hypothesis. So let us just go and see the table. How will we decide about the decision rule in this question? So this graph is showing you that this is the two-tailed test. So alpha, which was specified at 5%. So we will divide this 5% by 2 in order to get the probability for both the tails. So division of the alpha by 2, we get that 0.05 area will be in the left tail and the same 0.02 area on the right tail. So our decision rule or our depend upon two values now, the decision rule. Since our rejection region is in the both tail of the distribution, the left tail and the right tail. So if you just notice this right tail, it is the positive value of t, and with the left tail it is the negative value of t. However, the value will be same. So this is 2.262, the critical value. I will just show in a couple of minutes that how will we attain this 2.262 from the t table. Since t distribution is symmetric, so this value will be negatively right here on this left tail. So we will compare our value which we have computed from the sample, that is 4 point something. We will compare it with the 2.262 and minus 2.262, and this is the rule of comparison. If that t value is greater than the positive value in the table or it is less than the negative value of table, in both cases we are going to reject the null hypothesis. However, in this case our t value is significantly greater than 2.262. It is 4 point something, so it is greater than this 2.262. So therefore we are going to reject the null hypothesis at 5% level of significance, and rejecting the null hypothesis leads us to conclude that exercise significantly affects the level of lactic acid in the blood at 5% level of significance. So it has changed the level of lactic acid, significantly changed. For if we are going to reject the null hypothesis, it means the results are significant. So significant means that the null hypothesis with equality sign have been rejected, and you are now concluding that exercise has changed the level of lactic acid in the blood at 5% level of significance. Let us see how we have taken that table value. As alpha was 0.05, so divided alpha by 2 since it's a two-tailed test, and degrees of freedom was n minus 1, that is 9. So here we go about the table value. Since alpha by 2, we need to look at the column of 0.025 this ones, and with the degree of freedom 9 we need to take the value at degree of freedom 9. So table value is 2.262. we will use this table value. Here we go the two-tail graph, and this table value is positive in the right tail and the same table value goes negative in the left tail. Here we go, t alpha by 2 and minus t alpha by 2. This is how we have taken the table value which was used in the last pair t test question. Okay, at the last we will see the confidence intervals for difference between population mean in all three cases. The first of all, the first case right here, you can see this is the confidence interval for difference between population means, that is mu1 minus mu2. This is the sample difference x1 bar minus x2 bar, and this is the table value taken at the degrees of freedom. When you use pool test, we will always use the table value, the two-tailed table value, for constructing the confidence intervals. And similarly the pooled variance and all these calculations, you can simply calculate the confidence interval by taking the table value of two-tailed test from that question. And if you're going to plus this number in x1 bar minus x2 bar, you will get the upper limit, and if you minus it, you will get the lower limit. So upper limit and lower limit will comprise of the confidence interval for mu1 minus mu2, and if you calculate 95% confidence interval, it means your alpha will be 5%, and 95% confidence interval for the difference between population means will be interpreted like this. We are 95% sure that the exact difference of two population mean will fall in this interval which we have calculated. Similarly, we can calculate the confidence interval in case of prime test, t prime test, and in case of t pair test. So we can use these formulas in order to evaluate the confidence intervals for a difference between population means in all three cases. Thank you very much.